Fractions converted to decimals will either terminate, as in the Part 1 video, where I showed basically two types of fractions. The first was fractions with power of 10 denominators. You can go from fraction to decimal very quickly. Even if the denominator is not a power of 10, you can go from fraction to decimal with long division, and here the process does terminate. You finished with a 5. The remainder was 0, so you don't have to go any further. With this video, I'll show the other possibility. That is, a repeating pattern is established. Starting with 3/11. This is 3 divided by 11. Obviously it doesn't fit. Put in the decimal, tell the world, and give yourself some zeros. 11 goes into 30 twice. Bring down your 0. 11 goes into 80 7 times. Bring down your 0. 11 goes into 30 2 times. Bring down your 0. 11 goes into 80 7 times. I could put in more zeros and keep bringing them down, but this pattern 2 7 2 7 is going to continue. You can put 3 dots at the end. This is called an ellipsis. It indicates that the numbers continue forever. In order to show the decimal representation of 3/11, we simply write 0.27 with a bar over the decimal numbers that repeat. So this says that the pattern 2 7 repeats forever. Converting 2/3 to a decimal, this is 2 divided by 3. Three goes into 20 6 times. Bring down a 0. 3 goes into 20 6 times. I could put more zeros and keep bringing them down, but this pattern continues. So to represent 2/3 as a decimal, simply write 6 with a bar over it. Now in converting 22/7 to a decimal, we have 22 divided by 7. Goes in 3 times. I need more digits. Put in the decimal, tell the world, load up on some zeros. Bring down a 0. 7 goes into 10 1 time. Bring down a 0. I could go a few more digits. Eventually this pattern will start to repeat. But rather than have to carry this out until the pattern repeats, I'm asked to round to the hundredths place. So I'll say a little bit about rounding and then we'll come back and do these two. So we'll look at a couple examples where we're asked to round to the tenths place. Let's say we'll take 3 7/78, and we'll also look at 3 72. If they want me to round to the tenths place, I like to underline the tenths place. And then you look at the next digit to decide if you round up or round down. Now of these two numbers, one of them we're going to round up and one of them we're going to round down. So I think you can probably anticipate, because 8 is pretty large, we round up. So this becomes 3.8. because 2 is pretty small, we round down, so this becomes 3.7. But obviously in math we need a way that's a bit more precise, and we have an assurance that it's balanced. So what we have here is everything up to the tenths place is identical, but the hundredths place, which is what we'll be looking at, we have all the possibilities, 0 through 9. The fair way to divide this up is to split it in half. So if you're looking at a 5 or greater, you round up. If you're looking at 4 or less, you round down. So we'll come back to these two. I like to underline the hundredths place. Remember, it's tenths, then hundredths. Looking at the next digit, it's 4 or less, so I'll round down. I'm going to say it's approximately equal to. If I was asked to round to the thousandths place, first I'll indicate the thousandths place. If you're not sure, you can put a 1 under the decimal and then a 0 under each digit until you've written 1,000. I like to underline the digit. You look at the next number, it's 5 or greater, and round up. For these three, we're asked to round to the thousandths place, so first we'll identify the thousandths place. So the third digit is the thousandths. I'll underline the thousandths and I'll look at the next digit. So when I look at the 2, that's 4 or less, we round down. So notice we dropped the 2, that's how we rounded down. The 8 stays the same. So I stand here and I look at the next digit, it's 5 or greater, so I round up. And by the way, the fact that it's negative doesn't affect how you round. So you just have to keep up with the negative. But instead of a 6, it's got to be a 7. Down here I stand at the thousandths place, I look at the next digit, it's 5 or greater, I have to round up. But when I round up, 9 becomes 10, which means I have to carry the 1. So this number becomes, this 4 becomes a 5, and because they've asked me to round to the thousandths place, I'm going to be sure to put in the 0, which is my thousandths place. Here we're asked to round to the ones place. You could also be asked to round to the next whole number. So I'll underline the ones place, even though it's pretty obvious where that is. I look at the next digit. If it's 5 or greater, I round up. I stand at the ones place. I look at the next digit. It's 5 or greater, so I round up. I stand at the ones place, look at the next digit. It's 4 or less, so I round down. And this negative has no effect on how you round. We'll be comparing these 4 different sets of decimals. We'll use an inequality sign or an equal sign to indicate how they're related. Quick review of what these signs mean. 5 is greater than 2, or 2 is less than 5. First we'll do these two positives, and then we'll deal with this negative. I'll show these negatives when we get down here. So comparing these two decimals, we proceed digit by digit. 4s are the same, 3s are the same. This is the first difference we encounter. So I'm comparing a 0 to a 1, and 1 is greater than 0. Looking at this example, the same. Where's the difference? Okay, this 3 is compared to this 2. Three is greater than 2. Now when both signs are negative, you actually have to flip these inequality signs, because a negative 2 is actually greater than a negative 5. You can think of it as, I'd rather be $2 in debt than $5 in debt. And again over here, negative 2 is greater than negative 5. If you think of this on the number line, a negative 2 is closer to 0 than a negative 5. So we move along looking for what digit is different, the 9 and the 8. So I like to underline the two digits I'm focused on. If these values were positive, I would say 9 is greater, but since they're negative, I'll mention real quick, if you had, let's say, a negative 17 and you were comparing that to a positive 4, the positive value is always greater. And finally on this one, looking for digits that are different, everything's the same up to the 6. Here they've written zeros, but here I could put zeros forever. It doesn't change the value. So even though they have trailing zeros, these two values are equal. If you'd like some practice with the topics covered in Part 2 of the introduction, as long as you're at my website, you can download a worksheet with a detailed answer key. I also have a review that covers both Part 1 and Part 2.